So if f is a continuous function, if we have a function that's continuous, then we have these uninteresting limits, because as the x value approaches a number, it's just going to approach the function value. So the way that we talk about a continuous function is we say if, this is, I just wanted to make sure I define it the same way that it is on your packet. So it would say is the limit as x approaches c of f of x is equal to f of c if and only if f of x is continuous at x equals c. Okay. So let's break that down a little bit. That means that if the limit as x approaches a certain value is equal to the function value, it makes sense that would be continuous, because as x approaches a value, you would expect the y values to be getting closer to that value. Now, there are some functions that do weird things, that have asymptotes like this. As x approaches 0 from either side, there is no function value at 0, so we're discontinuous at 0. So this is a really good calculus definition of continuity. So let's take a look at this last part here. So same function, but this time, let's see what value we're asking for. So it looks like we're asking for the value of 5. If you plug in 5 on the top, you get 25 minus 15 minus 10, which is 0. And on the bottom, you also get 0. Well, that's an issue because we don't like dividing by 0. So what we have to do is we have to do a little bit more work and see if we can make this a little bit different. So first of all, let's take a look and see what's actually going on here. So let's go back to Desmos. Keep those. It's right over here. So we're going to go back to our function. It looks like we have a hole there. So if we approach 5, what does it look like the y values are getting close to? Looks like they're getting close to 7, right? And from the other side as well, looks like they're getting close to 7 as I approach 5 with x. And if you actually go right to 5, let's see if Desmos is going to do it for me. See how it disappears there for just a second? Because it freaks out. It says, no, if you plug in 5 here, I get 0 over 0, so it doesn't actually give me a function value. But the thing about limits is limits are funny because they care about everything near the point. The only thing they don't care about at all is the actual point itself. So if there's a hole, even if it was filled in up here, like even if there's a dot up here somewhere, if there's a hole right there, the limit is just whatever value the y values are approaching as x gets close to that number. So functions are all about what's happening near this x value. So the closer I get to 5, the closer the y values get to 7. Even though it's undefined right at 5, it looks like that limit should be 7. Now, how can we prove that algebraically? So what I'm going to do is I'm going to do a little bit more work and see if I can make this a little bit prettier. So I'm going to factor the top, x and x. Factoring skills, have to pull those out of the bag. Bottom we got x minus 5. So negative 10 and negative 3. Looks like we need a negative 5 and a plus 2. Hey, these cancel out. This now makes sense why we have a line. It's x plus 2 everywhere except at 5, because that would be dividing by 0. So we had that line that had the hole in it. X plus 2 looks something like this, and then there's going to be that little hole at 5, 7. But the limit, as you approach 5, those y values are getting closer to 7, because if you plug 5 in now, hey, look at that, 5 plus 2 is 7. So how are we going to do this? What are our strategies? And I might be covering them up with some ink. So we'll see if we have to erase some stuff. I bet we will. So let's erase a few things here. And let's look through